Okay, so at this point we're working with, we finally got to chemical reactions. What you're seeing here is two hydrogen atoms, two hydrogen. If you see an arrow, that means reacts to form, and of course what we're producing out of that would be two molecules of water. The 2 is called a coefficient. The number that's written below, we refer to that as a subscript. The number in front, coefficient. And that refers to you have actually two molecules of hydrogen, like in this example, two molecules of water in this example. And then, of course, if you see a number like this written to the lower right-hand corner, that refers to how many atoms of that element. So in this case, we have two atoms. It's called a subscript. And then an arrow means reacts to form. So what you have on this side of this chemical equation, these are called the reactants. And then, of course, whatever we produce, in this case, two molecules of water, we would refer to as our products. So that's how you would read a simple chemical equation. They're not very complicated. Most of you pick up on that pretty fast. So reactants will be on the left, products after the arrow. That's obviously what we're producing. The arrow is reacts to form. Coefficient would be the big number in front of the molecule. And then, of course, a number written to the lower right-hand corner is your subscript. So anyway, that's about all there is to it in a chemical equation. Okay, we've already talked about this, reactants. That one only had one product is all we had, which, well, actually we had two. We had two molecules of water, so I guess we had two products. And here's where they're actually just showing the physical structures of two hydrogen molecules. One oxygen molecule reacts to form two molecules of water. Ball and stick model on that one. Okay, so here are, now we get into properties of water. Now there are several properties. Some of these we've talked about, some of these we haven't talked about. Water adheres to itself. It is cohesive. And of course, what happens there is you do get some hydrogen bonding between the water molecules. Water is polar, so you end up with what your book refers to as a electronegative, or electronegative element. In this case, oxygen tends to pull the hydrogen's electron closer to the oxygen. Therefore, it gives it a partial negative charge because oxygen is electronegative. It tends to pull those electrons. The hydrogens, of course, will be carrying a partial positive charge because the one hydrogen electron is spending a good deal of its time towards that electronegative oxygen. So both of the hydrogens are going to be partially positive. Well, if we have two water molecules or several water molecules, then we get this attraction between the partial positive end of one water molecule, which will be the hydrogen, will attract to the partial negative end of the oxygen of a second water molecule. So they call that a hydrogen bond, which we've been through, but just a reminder. Okay, so water is cohesive, it adheres to itself, it's going to adhere to other things. If you wash clothing, then of course you throw that clothing typically in the shower. Some people put it out on a clothesline, which actually I kind of like that. I kind of miss the days that we did that. You didn't put it in a dryer to dry. You know, you hung it out on a line. It had a kind of a neat, fresh, crisp smell and texture to it. You know, I mean, I remember the days before we actually had dryers. You guys don't remember that, but in clotheslines, y'all may not even know what that is, but anyway, I do remember that. So, you know, we have the water adhering to the fabric, so obviously you have to apply enough heat in order to break all the hydrogen bonds and vaporize all the water. So the water, of course, would no longer be there, and you would have dry towels and so forth. So clean, dry towels instead of smelly towels that you probably need to put in the washer. I don't remember when we used to beat the towels on the rocks, though. Okay, I don't have any recollection of that. Okay, just in case you were wondering. But because the hydrogen is going to adhere to itself, it is cohesive, you get this surface tension, and this will give you an example. This is what you call a water strider. It's a bug, and it's light enough that it does not break the hydrogen bonds between the water molecules, and it basically has the ability to walk on water. Jesus could do that. I have tried it. I've sunk every time. You know, get out of a boat. It's like, okay, I'm going to try it. No, I would sink every time. I try to be good for a day or two, you know, have good thoughts, you know what I'm saying? Just try to, you know, try to not be a bad person. It's so difficult for me to be that good. But obviously I didn't even accomplish it because I would just sink immediately. So I've kind of given up on being that good. So I guess I don't know what that means. That just tells you that if you go to hell, then you know I'll say hello. We'll see. Anyway, thermal energy associated with random movement of molecules. You know, we typically call that heat. The transfer from a warmer to a cooler body, as defined as heat. So what comes out of transferring that thermal energy from a warmer to a cooler environment, you know, you actually have heat that's given off from that. Temperature measures the intensity of heat. That's actually the difference. It's the speed of the molecules is the temperature. So there is a difference. So, you know, we have to absorb heat in order to break the hydrogen bonds. And then anytime you're forming hydrogen bonds, you're actually releasing heat. So if you're breaking the hydrogen bonds, you have to put energy into it, or as an example, maybe heat into it. Doesn't have to be heat. There are other ways to break those bonds. You could physically break them, but you could break them with magnetic energy. You could break them with electrical energy, but we're talking about heat here. So if you add heat into, say, like a pan of water, you know, in order to get that to boil, you're going to have to, and vaporize that water, you have to break the hydrogen bonds. They will never leave the pan and go out into the atmosphere. It's not ever going to form steam unless you break the hydrogen bonds. Pretty much common sense. You got to break them before they go off into the air and form the steam. You know, but to condense, like condensation, it's kind of humid around here right now because we've had some rain. So I don't know if you like to run or you know, work in the yard, but you know, you form a lot of sweat. Or if you're drinking, say, like a glass of just cold water, there is condensation that will form on the exterior of the water glass. And what happens is the moisture that you have in the air, it will begin to cool, and as it cools, the water molecules come close together, and of course they form hydrogen bonds. And as they form the hydrogen bonds, then you're actually releasing the heat out of that when they do that. It kind of seems a little awkward, but anyway, they do. Let's see. We've talked about all the rest of that. Okay, so we do have a large supply of water that does keep the temperatures relatively constant on the planet, which it has for a while. And of course, now we're in a little bit different situation. Global warming, which I don't know how fast that's going to occur, and that's really the question for me. Is I know it's going on, I see it, but how fast is that going to happen? Do I have to worry in my lifetime that I need to move to Montana in order to have water? Or, can I continue to live in West Texas in order to have water? I don't know. I don't know how fast that process is occurring. Of course, it just requires doing a little bit of research, which I will when I get ready to retire. It's like, well, where am I going to retire? Maybe I need to retire in Montana. Land is pretty cheap. Real estate is pretty cheap. So, buy a little ranchette, 50 acres with a little cabin in the middle of it, by a stream, and you've got water. You're gonna have it for my lifetime anyway. At least if you're in Montana, I have friends that seriously they look in Montana for places because they go, oh, global warming is happening so fast. I don't know. We better get out of here. Who knows? I do not know. And I would be concerned if I were your age. I would be looking into it. It's like, do I want to raise a family here? Do I want to get a job here and live here, or in this Southwest at all? Maybe I need to move a little bit further north. Maybe so. I can't tell you. I can't answer that. But notice it says water does resist temperature change. It does. It only takes 1 calorie, which is what calories are measured in. Calories are measured in the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. So if I wanted to increase the temperature of 1 gram of water, which is really 1 milliliter of water, so if I had 1 gram, which is 1 mil of water, so we'll put 1 gram or 1 milliliter water, okay, and I wanted to increase the temperature by 1 degree Celsius, and I only had 1 mil, which is not much, but to increase the temperature by 1 degree Celsius, this takes exactly 1 small c calorie to do that. That's how much heat would actually be required to change that temperature. Okay. But that's if we're somewhere between 100 degrees Celsius, which is boiling point of water, and 0 degrees Celsius. So if I want to go 1 degree from, say, 0 degrees to 1 degree Celsius, that takes exactly 1 calorie to do that. If I want to go from 1 to 2 degrees Celsius, it's another calorie. 3 is another calorie. So to go from 0 to 100, that takes exactly a total of 100 calories. But the interesting thing is, if I want to take 1 gram or 1 milliliter of water, we're still at 1 gram or 1 mil of water, and I want to vaporize it, I want it to go off as a vapor, I'm not even going to change the temperature. I'm going to keep it at 100 degrees Celsius, but we're going from a liquid form to a gas form. So this is water vapor. I don't change temperatures. I'm just going from liquid to a gas form. That's what that G stands for. That takes 539 calories for every gram or every milliliter of water. A huge heat. I That means you got to break. The hydrogen bonding is pretty strong when you get all the hydrogen bonds together. But to take, it seems like it takes a long time to boil water. So you turn the burner on high, and you put some water in a pan, put it on the burner. And it takes a long time for it to get to a point to where it's actually boiling, and then the steam comes off of that. Well, that's water vapor. So it's going from a liquid state to a gas state. But for every milliliter, it takes 530 mil to go off as a gas for every milliliter. That's a huge amount of heat being added. But to just go from 0 degrees liquid water to 100 degrees liquid water, that's only going to take 100 calories. It's 1 calorie for every 1 degree increase. So to go from 0 to 100, that's 100 calories. But then when you go from 100 degrees Celsius liquid water to 100 degrees Celsius gas water, you have to put in 539 calories per milliliter per gram. That's huge. So, it doesn't really want to go off as a liquid. You have to add a tremendous amount of heat in order to get it to do that. Same thing if you're trying to get it to freeze. It takes it a while to freeze. So if I want to take it and put it at 0 degrees solid, which is what we call ice. I'm not even changing the temperature. I'm just getting it to ice. I have to subtract 80 calories to get it to do that. So that is a tremendous amount of heat coming out of that to get it to become an ice. So it doesn't really want to go into ice form. It doesn't really want to go into a gas form. It wants to stay a liquid right here. That's where it tends to stay, which is good because you don't want ice to form in our blood, which is 91 to 92% water. You step outside, it's below freezing, which it does in the winter. It gets below freezing. So you step outside and, you may your papers out in the yard and you want to run out there and get it, and all you have on are your boxer underwear. Who cares? You just run out there and get it. Come back in. Well, if it weren't such that you had to remove 80 calories for every milliliter, that's a tremendous loss of heat. By the time you got out to the paper, that paper boy's just gonna pitch it. I don't think he puts a lot into it. It doesn't land like on your, it's not Leave It to Beaver. It doesn't land on your porch. It lands out, 2 inches from the sidewalk, and you have to run way out there to get it. By the time you got there to get it, you'd be frozen. You're mostly water. And your blood is, like I said, 91 to 92% water. You'd be, you couldn't make it very far at all. And when the temperature gets, it's not going to go above 100 degrees Celsius, which is 212 degrees Fahrenheit. It's never been 212 degrees Fahrenheit in Odessa. It gets up to 108, or 110 maybe, but 212 degrees Fahrenheit, no. We don't have to worry about our water vaporizing out of our body. That's not going to happen. But anyway, so it does tend to want to remain a liquid. This 539 calories, that's called heat of vaporization. Triangle means heat up. So in order to get it to vaporize, to go off as a gas, for every milliliter it takes 539 calories. Heat of vaporization. This 80 is what we call heat of fusion, to get it to fuse together into ice. So you look at that and you go, well, isn't that the same as the freezing point and the boiling point? Boiling point is 100 degrees Celsius. 100 degrees Celsius, it is boiling point. But the amount of heat that it takes to get it to vaporize is heat of vaporization. But yeah, that is a boiling point. Freezing point is 0 degrees Celsius, sure, but the amount of heat required to get it to become ice is heat of fusion. So a little bit of difference, but anyway. Okay, so interesting stuff. Like I say, it's life is mostly water. Our Earth is mostly water, and they do teach courses just on water. I know they do at Rice University. I don't know where else they do that, but someone thinks it's interesting. They offer an entire course on it. We can offer a course on whatever we want to. I wouldn't mind offering a course on botany because I enjoy botany quite a bit, or on native plants. I could probably teach a class on native plants. I don't know if I can. I might be able to get that one to make. But a lot of people interested in native plants. That's maybe something to think about. I've never thought about that till this moment. Anyway, so it does offer evaporative cooling. When you sweat, the reason you're going to sweat is it's going to take, when you sweat, the heat actually gets to the surface of your body. You want to keep it from the core. Now, the core is the interior of your body. And if you work out, you know what like working out the core is. But the core is basically the exterior, towards the exterior. You want the heat to come to the exterior of the body. So when you're working out, you're red, because all of the vessels on the surface of your body, they dilate. Bless you. They dilate. And that's so that we can pull the heat to the surface of the body. And then when it gets really hot on the surface, then the liquid that we have within the body, because there's liquid all over us, water, then that will come through pores. We call it sweat. And then because it's so hot, it will vaporize. The wind will go over it and it will vaporize. So not only are we pulling out the water, which is why we need to rehydrate and keep plenty of water when we exercise or work outside, because the water will come out. It will pull some of the salts out. It will also pull some of the waste material out of the body. Very good. That's why people go into a steam sauna or just a hot rock sauna. You get in there, you sweat. It's pulling out the wastes out of your body. It's very cleansing to do that. Exercise is very cleansing. That's why exercise, one of the reasons why exercise makes you feel good while you're doing it. Maybe you don't feel so good, but afterwards, you're going to feel pretty good. You get the waste out. That's good. And then you get also, you pull that heat out and the water vaporizes off your body. It evaporates, and then, of course, you're cooler because of that. And this may be a little bit disgusting, but the composition of sweat is very close to the composition of urine. Very, very close. Now, there are some differences in concentration of, say, nitrogen waste in sweat and nitrogen waste that you have in urine. There's less nitrogen waste that you have in the sweat than the nitrogen waste that you have in the urine. But as far as the composition, what's in it, very similar, which is kind of weird. So when you sweat, you're basically just urinating on your body. But I will also say urine is sterile. It's absolutely sterile. Absolutely sterile. We are kind of raised where we think urine is some nasty material. Well, urine really isn't, because it is sterile. When it comes out of your body, there are no bacteria, there are no viruses, there's nothing in it that could possibly harm you. In fact, it has a lot of ammonia. Ammonia is a cleansing agent. It's not bad stuff. But most of us, after we urinate, we go wash our hands. Now, feces are definitely full of bacteria, certainly. That is nasty stuff. But when it comes to urine, no, it's sterile. Of course, we still wash our hands. We've been taught to do that. It's kind of built into us. They teach us when we're young, and so that's what we do. Anyway, look at the steam rising off this guy. That's what you call evaporative cooling right there. That's amazing, crazy. Okay, so we have already discussed the three forms of water, our three states. We have solid, liquid, gas for water. The solid, of course, is the ice. The gas is the water vapor. Water is less dense as a solid than it is as a liquid. And we did talk about it. It's most dense at 4 degrees Celsius. That bond angle is like this. And then when you go below 4, say like you go to 3 degrees Celsius, it starts doing this. And then 2 degrees, and then 1 degree, and then 0 degrees, it goes out. So at 0 degrees, which is when water freezes, then ice is going to float. And we've already talked about that, but it does float because the bond angle changes. Most things will not do that. You don't reach the smallest bond angle at, say, until you get to freezing point. Water's different. You get the shortest bond angle at 4 degrees Celsius, and then when you get to freezing point, the bond angle, oxygen would be my head, and at the end of my hands would be the hydrogens. You get a really large bond angle, so it's going to float on top of that water, which is cool, which is good. That's what we want. So, and when it freezes, you do form stable hydrogen bonds. It'll show you that right here. So look at the bond angle just with the water itself first, bond angle, and then notice the bond angle is larger when you get into the ice. And here's a polar bear probably floating on the one last piece of ice left in the Arctic before it all melts away. That is so horrible. It just kills me. Okay, now it is also an excellent solvent. Now these are all properties of water, and I've been doing some of the grading when you guys are answering your discussion questions, and I do know that there are some problems in doing that, and we're trying to get all that corrected. Some people are not able to get on there and answer those. I'm in contact with the person who's head of all of Blackboard. I mean, this lady knows Blackboard inside and out, and she goes, there should be no problem, there should be no problem, but there still is some problem. And she's a little baffled by it, but we'll get it fixed, or she'll get it fixed. I know her well enough to know she will work with it until she gets it fixed. So if you're having a problem posting something, just keep at it. I would bet within an hour or two it will be fixed. I just emailed her a few minutes ago. So it's a solvent. A solvent does the solution. Does the dissolving. Whatever does the dissolving is a solvent. Okay, so if I want to put sugar in water, sugar will be the solvent. Whatever gets dissolved is a solute. It's whatever gets dissolved. So if I have dissolved a solute like sugar or salt into water, because water is my solvent, it's what did the dissolving. This is what you call an aqueous solution. Now some things do not dissolve in water. Oil does not dissolve in water. If you have oil stains on your driveway, then obviously you can spray it with water all you want, or on the wheels of your automobile. I don't know about you, but I would really like my wheels to be nice and shiny and look good. I don't always clean them probably as well as I should and as often as I should. But nonetheless, if you spray that, they sell several products. One of them is called Simple Green. You can spray that on a little commercial here. Purple Power. Purple Power is really good too. It's less expensive than Simple Green. You can put a little spray bottle in, and before you ever go through like a laser wash, you may do it all by hand, I don't know. I just spray it on my wheels, and then I go through a laser wash, and it's just you come, you're pretty sparkling on your wheels. You don't have to put in a lot of effort to clean it all up, finish it up, make it all look good. And same thing with if you get bugs on the front end of your automobile, which I do a lot because I go back and forth to Alpine pretty much on a weekly basis. You spray that on the grill and go through a laser wash, shazam, bugs are gone. Do not spray it on your license plates. It will dissolve the print, and therefore you will not have license plates that are legible, and so you might get stopped. And I don't know about you, but one thing I don't want to be is stopped by a highway patrolman. There are times that could really not be a good thing. So I try to avoid that at all costs. Drive the speed limit. Always, try to, stay between the lines. You know what I'm talking about. Okay. Very, very serious about that. The solvent? Yeah, it's called Purple Power. I'm sorry. What did you say? No, if I did, I said that wrong. The solvent is whatever does the dissolving. So water would be the solvent and sugar would be the solute. Whatever gets dissolved is the solute. So salt would be a solute. Sugar would be a solute. In the case of cleaning your wheels, the Purple Power would be the solvent because it will dissolve the grease and brake dust that you have on your wheels. And so that brake dust and whatever you have on your wheels is a solute. That's what you're trying to dissolve. Yeah. And you don't want to dissolve the ink off your license plate with Purple Power. Not a good thing at all. You'll be stopped. And there are times when I just don't want to be stopped. Probably ever. I just don't want to be stopped. Okay. So if it's something polar like water, we know is polar, it's going to dissolve polar solutes. For example, salt is polar. We know sodium is positive, chlorine is negative. It will dissolve that. A lot of oxygen in sugar. You don't know it yet, but we'll look at it. And you'll go, yep, lots of oxygen. Anytime you have oxygen, oxygen is electronegative. It pulls the electrons from other things, which means wherever it's getting the electron, that thing that it pulled the electron from is going to be positive, or at least partially positive. And the oxygen is pulling the electron, so the oxygen will be partially negative. So anytime you have oxygen or those elements in the upper right-hand corner of your periodic table, you're dealing with electronegativity on those. Okay, and this is just showing you what they call a hydration shell. I think this is pretty cool. When you put salt in water and you dissolve it, don't you always think, where did it go? Where is it? I don't see it. When I pour it in there, I see it. Or you put sugar in water and you go, where is it? I don't see it. It's no longer in there. Well, notice what happens. That water forms a complete shell around the part negative or the positive part that you're working with. So water will be attracted. In this case, chlorine is negative, so the partially positive hydrogens are attracted to that negative. They're partially positive. The oxygen's partially negative, so the hydrogens are attracted here because they're partially positive. And the sodium, which is positive, all the negatively or partially negative oxygens are going to be attracted to that positive sodium. So the oxygens are partially negative, that will attract to the positive. And so you've got these hydration shells that go all the way around that ion. You're not going to see it. You will not see it. That's why you don't see it. Most people couldn't tell you that. They're like, well, I don't know. Where is it? And of course, it takes a little bit of an education in order to be able to understand why you don't see that in there. It's not a huge amount of education, but a little bit, and then it totally makes sense. I think education's cool. It's like you have questions, and you get those answered. I don't know. I'm just curious. I want to know some answers, and it's not that difficult to understand those concepts. Okay, acids and bases. Acids are going to release. Now, there are lots of different acids out there, like hydrochloric acid, HCl. Now, chlorine is a very electronegative. Hydrogen will lose its electron to chlorine because it picks up the one electron that hydrogen has. That is an acid. Now, if you put acids in water, it will actually break up that going into water. Now, because water is polar, you will break it up and you will form ions, which means you will break the hydrogen away from the chlorine. The water will break this. And any substance that releases the hydrogen ion, which is what this is called, the hydrogen ion, so anything that releases the hydrogen ion is going to be an acid. And the reason they call it a hydrogen ion, you have hydrogen, you have one proton and one electron. That's a complete hydrogen. But if I take the electron off of it, the only thing I have is a proton. I don't have the electron going around. I pulled the electron off. So that is really a hydrogen with a positive charge. So if I have the positive and the negative, the proton and the electron, they cancel. But if all I have is the proton, I don't have a negative charge to cancel out that positive charge. Plus. It's the hydrogen ion. Where did that electron go? I already said, well, chlorine picked it up. Got it. But if I put it in water, those two are going to split up, the hydrogen and the chlorine. So anything that releases the hydrogen ion is going to be a base, an acid. Bases are things that pick up hydrogen ions. They attract hydrogen ions. For example, this is probably your most common base, NaOH. Sodium is positive. The hydroxide is called, the OH is called a hydroxide. That's negative. And so if I put that in water, add that to water, what actually happens there is it's going to break up, and you'll have a sodium which will combine with, let's see, sodium, plus, then you'll release the OH, which is negative, but the hydrogen ion will attract to that. All right. So, of course, when it does, what you're making out of that would be water. So, this is why acids and bases, if you mix those in equal proportions, you end up with something that's neutral. It is not at all. It's not at all positive or negative. And then also the sodium will attract to the chlorine. And of course, what that forms is the sodium chloride. So when you add acids and bases, you really get, it should actually look like this. Sodium chloride, table salt, plus you get water. So anytime you mix an acid with a base, the base unit, which is the negative unit, will attract the hydrogen. And this is the most common base unit, this OH, with a negative charge. It will attract that positive hydrogen and form water. And of course, what you're left with is the sodium, and that will attract to the negative chlorine, and you form salt. So anytime you add acid plus base, what you really get, acid plus a base, what comes out of that is a salt plus water. That's it. Acid plus base, salt and water. And you can see that. If you follow the arrows, you can see how that would happen. So acids release the hydrogen ion. That makes them acids. They automatically release that in water. And bases will release a base unit. Now, OH is the most common base unit. So, sodium hydroxide, that's what they put in soap. That's what makes soap really gooey, very gooey for some reason. So, if you've got if you're, like using a shower gel or shampoo or, any of those substances, you're dealing with a base unit. You're dealing with a base. Even detergent. If you put detergent, like dishwashing detergent, is gooey. If you have laundry detergent, it's in like a solid form. But if you just put a little bit of it in water and mix it up, it'll be gooey. Have a gooiness to it. That's unit, the base. Okay, let's talk about this pH scale. pH actually stands for, everybody have this? Or cool? All right, good. pH, this means something. pH means power of the hydrogen ion. Power of. Okay, so power of. What is 10 to the power of 3? 10 times 10 times 10. What is that? 1,000. What's 10 to the power of 2? Okay, so that just means how many hydrogens do I have? That's all. That's what pH stands for. Power of the hydrogen ion. That's the P and that's the H. H stands for the hydrogen ion. P stands for power. Power of the hydrogen ion. And for some reason, people never picked that up in high school. I'm like, what? I mean, it's the pH. You don't even know what that means? They don't have a clue. How many of you knew that? Power of the hydrogen ion. You got a diploma, didn't you? You walked across the stage. They gave you a diploma. Your parents were there, your grandparents, your brothers and sisters, and they all clapped, and they all gave you a. No? Okay. You got a new car out of it? No. Some people do. I wasn't one of the lucky ones. Like, new car? What are you kidding? Oh, yeah, Camaro. Yeah, sure. Right. No. Didn't happen. Did not happen. Anyway, the pH scale runs anywhere from 0, and some people think it starts at 1. It doesn't. It starts at 0. All the way to 14. So let's see if we can write all this out. 1, 2, 3. All right, made it a little bit too long, which is unusual. Usually I make it too short. Okay, so the pH scale runs all the way from 0 to 14. pH 7 is neutral. All right, so that is neutral, meaning the number of hydrogen ions will always equal the number of hydroxide. Okay. Well, if I combined a hydrogen and an OH, I'd have H2O. What is that? Water's neutral. Now, I'm not saying the water that we get out of our faucets will be neutral. That would be a different situation. I don't, I may shower in that because my skin is totally repellent of water. Okay? So I don't mind if it gets on my skin. I am not drinking it. I do not fill my cat's water bowl with it. No, they're not getting that. They're getting RO water. I'm not letting them drink this stuff. We're getting, as they call water, coming out of the faucet. Not happening. It's not fit to drink. It just isn't. There are particles in there that I don't know. I would say the city of Odessa would say, yeah, it was fit to drink. But there are those who will say, no, it is not. Anything less, when you start going below pH 7, so you're at a 6.99999, it's an acid. The lower the number, below 7, the more acidic. So acidity increases the lower the number. Okay, now I'll show you how that works. If we drop from a pH 7 down to a pH 6, we have 10 times more hydrogen ions than we do hydroxyls. So we just have the one hydroxyl, just the one. Okay. 10 times more hydrogens. I better put parentheses around there. All right. Oh, I did screw that up totally. We have 10 times more hydrogens than we do base units, whatever that base unit would be. Okay. Correct the mistake. There. So at a pH of 6, we have 10 times more hydrogen ions than we do base units. There's only one of those. Okay, at a pH 5, I have 100 times, or 10 to the power 2, hydrogen ions, and only one hydroxyl base. At a pH of 4, I have 1,000 times hydrogens to one hydroxyl. So every time you go from below 7, one whole number, now you could have a pH of 6.5 or 6.7 or whatever, but I'm just saying one whole number, you increase your hydrogen ion concentration 10 times. Every time we go above pH 7, you're increasing your base unit. This is called base. Sometimes they call it alkalinity. Base and alkalinity, they're equivalents. They're the same. You don't see this term a whole lot, alkalinity, but it's just a different term for base. All right, so if I go to a pH of 8, I will only have one hydrogen, and I will have 10 hydroxyls. I have 10 times the base unit. If I go to a pH of 9, I'm going to increase my base unit even 10 more times. So I have one hydrogen, and I would have 10 to the power 2, which is 100 instead of 10 base units. At a pH of 10, I increase my base unit even 10 more times. So I'd have one hydrogen to 1,000 base units. All right, and you can continue that all across the board if you wanted to, but every time you increase, you know, like from 4 to 3, you're decreasing, or you're increasing your acidity, so that'd be 10 to the power of 4 hydrogens and only one base unit. If you go from 10 to 11, you're increasing your base unit from one hydrogen ion to 10 to the power of 4 base units. So you're increasing your base unit by 10 times. And that happens with every 1 degree increase, 1 degree decrease is really the way to look at that. So this is why they call it the power of the hydrogen ion. You know, acids, bases, pH, they're not that complicated when you really look at that. Once you understand, this means power up. And by the way, that P is a small p and that H is a capital H because that stands for the hydrogen ion. So it is pH, small p, capital H. If you ever write it like this, capital P, capital H, that is wrong. If you ever write it capital P, small h, that means someone who has a doctorate degree, PhD, you know. So that would be wrong as well, but it should always be written like this. If you write it this way or this way, it's wrong. It's just wrong. You just miss some credit. So don't do that. Get it right. Get an education. That's what you need. It'll get you where you need to go. It's not hard. It's, you know, I know it's not easy, It does take time. It does take effort, but that's what you have to do. Okay, we're out of time. I wish we had about 4 more hours today. That would be great, but we don't. I know you don't wish that. I could certainly use it. All right, have a good day. Oh,